Hello and welcome, dear students, to the course Physical Chemistry. Today we begin our academic journey into the world of physical chemistry. Our first stop is this module, which is appropriately called Introduction to Physical Chemistry. Ancient Romans used to say nomen est omen, which means the name is a sign. While it may not always apply to people, this is an idea behind the naming of scientific disciplines. Let's look then, what's in the name of our discipline, physical chemistry. This name is a combination of two parts, the noun chemistry and the adjective physical. First, let's consider chemistry. The core of chemistry is the study of the composition and transformations of chemical substances. These substances are built by atoms, which are the smallest units of matter in chemistry. During a chemical reaction, atoms don't change. In addition to this, chemistry also explores the physical properties of substances and materials composed of different substances. However, the primary emphasis in chemistry always lies on chemical substances. Next, let's understand the term physical. Physics may seem difficult to define because it is a vast and comprehensive field. Physics can be considered the foundation of all natural sciences. Historically, physics was the name of the original natural science in the time of ancient Greeks. More or less all other natural sciences branched out of physics. We understand physics now as the branch of science that studies the most fundamental principles of matter, energy, and their interactions. The main focus in physics is on these fundamental principles that govern natural phenomena. When these two terms are combined to form physical chemistry, we get a branch of chemistry that is underpinned by physics. This implies using the principles, concepts, theories, models, and mathematical apparatus of physics to study chemical substances and their transformations. We also borrow experimental techniques and methodologies from physics, such as various types of spectroscopies to characterize substances. These methods, often referred to as analytical techniques, follow a particular pattern in their development. They usually start as revolutionary techniques developed by physicists to illustrate a new principle or understand nature. Over time, these techniques become standard methods for measuring specific physical properties of chemical substances. Physical chemistry, as we saw in the previous slide, isn't a single unified subject. Rather, it is a wide-ranging subject that encompasses a variety of distinct but interrelated subfields. Let's explore this scientific landscape to understand how these areas interact with and build upon one another. This will provide a comprehensive picture of the scope of physical chemistry. Our journey through the landscape of physical chemistry begins with the cornerstone of this discipline, classical thermodynamics. We start with the fundamental concept of thermodynamic equilibrium and explore the state of a system and its relationship to the energy transfer between the system and its surroundings. Thermodynamics is underpinned by two basic principles. The first law, the principle of energy conservation, states that energy can neither be created nor destroyed, only transformed. The second law serves as a guide to determine which state changes are allowed, ruling out certain possibilities even if the energy balance permits them. Together, these laws govern the universe. They provide a framework for understanding the direction of spontaneous change in a system state and identifying the equilibrium state to which the system naturally strives. Statistical thermodynamics extends classical thermodynamics into the theoretical realm. It employs statistical methods to derive the thermodynamic properties of a system from the properties of its microscopic constituents. This discipline forms a bridge between the microscopic world of atoms and molecules and the macroscopic world of classical thermodynamics. It provides theoretical explanations for many statements in classical thermodynamics, which are originally formulated based on experimental observations. Statistical thermodynamics is marked with an ellipse here because it is not a part of this course. Nonetheless, understanding a few key concepts from statistical thermodynamics will help you in grasping some key aspects of the classical thermodynamics. Next, we will advance into chemical thermodynamics. This area builds upon the foundation of classical thermodynamics, applying its principles to chemical reactions and substances. We are going to explore equilibrium states in various contexts, such as chemical reactions, phase transitions, and mixtures of different substances. Furthermore, we will understand how these equilibrium states can be influenced and controlled by external parameters like temperature and pressure. After exploring chemical thermodynamics, we shift our attention to chemical kinetics. While thermodynamics tells us the final state that a system strives to achieve, kinetics provides us with insights into how quickly it reaches this state. Chemical kinetics is a rather broad field dealing with the study of reaction rates and how these rates change under different conditions. We will also look into the mechanism by which reactions occur, from simple single-step reactions to complex multi-step mechanisms. An important part of chemical kinetics is the study of transport phenomena, understanding how molecules move in various mediums, which can be also crucial for determining reaction rates. Our exploration of chemical kinetics will deepen our understanding of how and why reactions happen at the pace they do. As the next field in this landscape, we introduce spectroscopy. This domain encompasses a variety of techniques dedicated to the study of the interaction between matter and light, and sometimes examining how matter produces light itself. These techniques offer crucial insights into a variety of properties, including structure, dynamics, and thermodynamic characteristics of molecules. Moreover, spectroscopy is instrumental in studying both reaction rates and mechanisms, further deepening our understanding of chemical processes. At this step, we would like to place quantum chemistry on the landscape of physical chemistry. Quantum chemistry applies the principles of quantum mechanics to chemical systems. It provides a theoretical foundation for the understanding of chemical bonding, reaction mechanisms, and the interaction of molecules with light. These are topics that are fundamental to other subfields of physical chemistry. Quantum chemistry is also marked with an ellipse here because it is not a part of the course. Nevertheless, we will build some connections between our major topics and quantum chemistry. Surface chemistry studies chemical processes that occur at the surfaces of solid substances. It all begins with adsorption, the attachment of molecules or ions from a gas phase or liquid solution to a surface of the substrate. This basic phenomenon is the foundation of many surface-confined chemical reactions. There are both thermodynamic and kinetic aspects of surface chemistry. Various spectroscopic methods are also widely employed to investigate the characteristics of adsorbed species, the nature of active sites on the surface, and the mechanisms of surface reactions. Moving forward, we come across electrochemistry. This subfield of physical chemistry deals with the relationship between electricity and chemical reactions. We will focus here on redox reactions involving the transfer of electrons between a solid electrode and species in a solution. As there are solid surfaces involved, a connection with surface chemistry is imminent. There are both thermodynamic and kinetic aspects of electrochemistry, as we seek to understand not only which reactions are possible, but also how quickly they occur. As we near the end of our journey through the landscape of physical chemistry, we encounter the field of catalysis. This specialized subdomain of chemical kinetics is devoted to the study of catalysts, substances that speed up chemical reactions without being consumed. Catalysis deals with a variety of systems. In homogeneous catalysis, the catalyst is located in the same phase as the reactants. On the other hand, heterogeneous catalysis studies catalytic processes where the reactants and the catalyst are located in different phases. In this case, the key processes occur at the interface, creating an intrinsic link with surface chemistry. When the catalyzed reaction involves an electrochemical process, we are looking at electrocatalysis. And of course, an array of spectroscopic methods is employed to probe catalytic processes, providing us with deeper insights into their nature and mechanisms. Finally, we have reached the last stop of today's journey through the landscape of physical chemistry, enzyme catalysis. Enzymes are biological catalysts that greatly enhance the rate of almost all chemical reactions occurring inside living cells. This subject is a multidisciplinary field bringing together various areas of natural scientists. As physical chemists, our focus is on examining this topic from a physico-chemical perspective. We will discuss the mechanisms of reactions catalyzed by enzymes and how these reactions can be studied using tools and methods of physical chemistry. With that, we conclude our first overview of the landscape of physical chemistry. We have traversed various fields, from classical thermodynamics to enzyme catalysis, each with its unique relevance and perspective. As we move forward in this course, we will advance into these topics, not as isolated domains, but as interconnected elements of a larger whole. This approach will provide a comprehensive understanding of physical chemistry. We hope you are looking forward to embark on this exploration of the principles that underlie the chemical phenomena that we encounter in our daily life and the natural world around us.